Hi everyone, so we are from group 4. We will talk about the case study palliative cancer, which is cancer prostate, symptomatic lumbar spine mets, and this patient has been planned for 20 gray over 5 fractions. However, in fraction 1, during its delivered, it is delivered at 80 cm SSD rather than 100 cm SSD. So what are the implications of this? And what would you do? So we will explain about it later, and we will explain to you about the target volume, shielding organ at risk, the dose distribution, which also included on what happen if the fraction is delivered at 80 cm SSD rather than 100 cm SSD, beam arrangements, and its reasons. Target volume. For target volume, we will talk about GTV, CTV, and PTV. So for GTV is vertebral and soft tissue tumor as seen on diagnostic MRI. CTV, spinal canal, the width of the vertebrae and one vertebrae above and below the SCC if the planing is based on MRI, and PTV, which is CTV plus 1 cm. Shielding organ at risk. Organ at risk. First, right and left kidney. Use shielding block. 2. Spinal cord. 3. Liver. 4. Ribs. And 5. Stomach. For spinal cord, liver, ribs, and stomach, use smaller field size and shield other unnecessary organ using MLC or other shielding. Fraction 1 is delivered at 80 cm SSD rather than 100 cm SSD. What is the solution for this problem? Before solving this problem, we need to know what are the factors that involve, which are PDD, PAR, Bmax, isodose curves, and beam modification device. Source to skin distance SSD is the distance from the source or target of the treatment machine to the surface of the patient. Isocenter established at the patient's skin surface. When the gantry rotates around the patient, the SSD will continually change. Dose calculation often at Dmax. Field size set on the collimator will be the same measured at the patient's skin. Dmax. Dmax is the point where dose reaches its maximum value. Mainly depends on the energy of the beam. The depth of maximum ionization increase as the energy of the beam increase. Factors influence field size and distance. Dose rate. Dose rate, as the changing the field size, distance, or attenuating medium will change the dose rate. If the distance increase, dose rate decrease due to ISL, which is inverse square law. PDD, percent depth dose, is the ratio expressed as a percentage of the absorbed dose at a given depth to the absorbed dose at a fixed reference depth, usually Dmax. Most commonly used for fixed SSD treatments. Dependence on energy. The increasing the energy, the more penetrating, the more PDD. The higher the depth, the lower the PDD due to attenuation through metal. The larger the field size, the more scatter, the higher the PDD. The higher the SSD, the higher the PDD, and also the inverse square law. The percentage depth dose
beyond the depth of maximum dose increases with beam energy. Higher energy beams have greater penetrating power and thus deliver a higher percentage depth dose. Because percent depth dose determines how much dose can be delivered at depth relative to the surface dose or dm, the SSD needs to be as large as possible. So this is the formula of the PDD. Conversion of percent depth dose from one SSD to another, the PAR method, is called Maynard F factor. It is based on the interrelationship between percent depth dose and PAR. So this is the formula for PAR and F. The isosceles chart is the family of isosceles curves usually drawn at equal increments of percent depth dose, representing the variation in dose as a function of depth and transverse distance from central axis. Applicable when the patient is treated at the constant source-to-surface distance, SSD. Flattening filter. Flattening filter determining the shape of the isosceles curves. Without this filter, the isosceles curves will be conical in shape, showing markedly increased X-ray intensity along the central axis and a rapid reduction transversely. The function makes the beam intensity distribution relatively uniform across the field, which is flat. Therefore, the filter is thickest in the middle and tapers off toward the edge. So, this diagram A, shows the SSD normalized at Dmax 100 cm. Diagram B shows SSD normalized at depth, which is isocenter 80 cm. Based on these isosceles curves, we can see that there are two SSD which are 180 cm. For this case, if the patient is treated with SSD 80 cm, then he will not receive 100% prescribed dose. This is due to the photon that received is not entirely on the Dmax. There will be not much implication to this patient because usually for palliative, there will be 5 fractions, and for other fractions, we can use the correction method by using the correlation between PAR and PDD by using certain equation that can be calculated by using computer. Beam arrangements. Figure 1 shows the conformal plan for the spinal irradiation in single posterior field, APPA field, and 3D conformal involve multiple fields. By referring to the measurements ICRU report 50, the conformal plan for single posterior field can be concluded that the plan do not comply with the ICRU 50 recommendations for PTV dose distribution. Meanwhile, for APPA fields, plans did attain the intended dose range with homogeneous distribution and reasonable dose to the medulla, spinalis, esophagus, and intestines. Compare between the APPA field and 3D conformal that included a fair set of oblique field. The deposition of radiation within kidneys will be higher in 3D conformal that included oblique field. In conclusion, APPA fields will give the best dose distribution to the tumor volume and less radiation damage to the organ at risk around the treatment area.
Created using Powtoon.